Da Silva and Luis Guzman.
Luis Gonzalez.
Gonzalez? SigFLUP has been an Australian Labor Party member of the Australian Senate, representing the state of Tasmania since August 2000. She comes from a family with a long labor tradition. Her grandmother was a founding member of the Hobart branch of the ALP, and her late uncle was a Tasmanian state ALP president. Luis Gonzalez is a Haitian... I don't even know what this says. Agronomist? And founder of an environmental peasant movement. He received the Goldman Environmental Prize in 2005 for his work on forest protection.
Thank you. Thanks for coming. This is the last presentation. I'm glad you're coming, and after this, we can all breathe a big sigh of relief and wait for block party. So let me start a video. Hopefully it doesn't wig out on the size, but we'll see. First, I believe.
Hey, nerd! Tired of playing with that old, dumb 8-bit console? Uh-huh. We'll try putting some attitude into your console, dude!
Sega Genesis with its 16-bit graphics and blast processing is here to show the other consoles who's boss. Sorry guys, but you can't do this on Nintendo.
What? Genesis does what Nintendo don't.
All right, round of applause for the Sega Genesis. How many of you had this console growing up? How many of you played the Sega Genesis? Can I see some hands? A good number of people, maybe 70% of people in the room. Anyone have the console now? Cool, we have a couple over there and one over here. Does anyone have a flash cart or something? Does anyone play ROMs on their Sega Genesis? I'm sorry? You say your Xbox, oh, I see what you're saying. So it's kind of like a prize, sort of a treasure. She collects antique consoles. That's kind of an interesting concept. I don't know, like, my thing with Sega Genesis and a lot of people collect antique consoles, but a lot of things are emulated, you know? So you have run things on an emulator, and so you want to play a ROM, you download a ROM and you play it on an emulator. You don't burn it to, you don't write it to a flash or a ROM or anything like that and play it on a Sega Genesis. No one really does that. So the hardware becomes an emulator. An emulator isn't real hardware. It's a representation of what someone's opinion of what the hardware is. But that's what everyone runs. And then you have other emulators that are written, and when they write the emulators, I wrote a Nintendo emulator, and this is what I did. I looked to other emulators to write it. And so I wrote it based on other emulators, and it becomes this bizarro incestual sort of thing. Like that commercial isn't a Sega Genesis commercial. I found that on YouTube. And so it's like someone representing, as they would in an emulator, this Sega Genesis, whether it be its marketing or its commercials or the actual hardware with something else. It's kind of a funny concept, and kind of a concept that you have to look out for when you start to program the Sega Genesis, because you may find that something will work in an emulator, it won't work on a Sega. Something will work in one emulator, it won't work in another emulator. We're all talking about something that's supposed to be static, right? But it's not, because no one uses emulators. I don't know. I think it's kind of a weird concept, but we're gonna skip we're just gonna go straight to the hardware pretty much and just talk about that on an emulator. Let me X-Randar this back, because I figured it would do that. So this is Sega Genesis. It looks complicated as fuck. And maybe if you took it and smashed it on the ground, this is what it would look like. But you got your cartridge here, you got your controller, and your television. And you got like 3 main sort of areas that you can sort of make out there. The 2 of them are processors. We have 2 processors in the Sega Genesis, the 68K, the 68000. I like to say 68K. So whenever I say that, I mean the 68000. It's a 16-bit processor with a lot of 32-bit instructions, 16-bit data bus, just an overall pretty elite processor. Then we got the Z80, which is kind of a 16-bit processor too, 8-bit data bus, a lot of 16-bit registers and things like that. This is the 68K, this is the Z80. And then finally got this little guy here. This is the VDP, or the video display processor, which draws everything. That's why I attached to the TV there. So every device here has memory associated with it. And we're representing the memory in sort of a linear graph, Y being lowest address to high Y being the highest address. It's a memory map. And so we have 2 main memory maps, one for the Z80, one for the 68K. And they are connected. So this is the 68K, as you can see by these squiggly lines here. It's connected to the Z80 memory, and it's a direct map to the memory. There's an area in the 68K memory that, if you write to it, you're addressing Z80 memory. You have to do funky things to do that, but basically that's what you do. And then you got VDP over here with 3 different memories, and the way you communicate to it is through registers. And the registers are represented in the 68K's memory through a couple of addresses, one for control, one for data. Let me pull up some bigger picture of the 68K, and maybe you can see that in a little more detail. This is the 68K. I don't know if you remember the picture, but the top here was connected to Power Rangers. Not a cartridge I played, but a cartridge that is pretty big nonetheless. It could be as big as 4 megabytes. We have 0 through this address here is where the ROM is mapped onto the 68K. And for all intents and purposes, that's where the program starts. At the beginning of the memory, there's an interrupt table. And in that interrupt table, you are pointed to where to start. And it doesn't really work that way in hardware because it actually runs a ROM, which checks to see if the word Sega is in a certain place in that ROM, so that if you change that, you violate some law that they can enforce, some sort of trademark violation or something like that. So that's kind of how it's not a technological sort of this does not have the seal of quality control, but well, the Nintendo, just sidetracking a little bit, the Nintendo, so I heard this earlier from the guy who melts chips. Maybe you saw his thing, but he's talking about how some of the unsupported cartridges, like Bible Adventures for the Nintendo had a little tiny 4-bit processor, like a microcontroller, one of the cartridge, one of the Nintendo talking to each other to negotiate, let's start the fucking thing because you're a legitimate cartridge. While the unlegitimate cartridges, like Bible Adventures, said fuck that and blew the chip up inside the Sega. Some voltage something or something, I don't know the details of it, but I thought that was particularly clever. It's not like that in the Sega Genesis. You just look for Sega, and then your little lawyer's sick after you if you violate that. I don't know what it is nowadays, but whatever. Blue areas we don't use. We don't use a lot of areas. Actually, you can use a lot of areas, but I don't use a lot of areas, so I'm not going to care about them too much. This area right here is where the Z80 is mapped. You have the squigglies going down to the Z80. After that, we have a little area here, which I didn't represent with numbers, unfortunately. That is mapped to the controller. This little squiggly goes down to the controller. And this is a similar interface as this, where you have registers that you write to. It's a little bit different. Nothing. Then you got this sweet little area. That's where those 2 addresses are. Well, those 8 addresses, but one's 32-bit, one's 16-bit. So I guess not all 8 addresses, but whatever, that's where those 2 things are. Then you got 64K of RAM, which you can pretty much do anything with right here. The RAM is mirrored, and everything's mirrored in the blue area, and there's all sorts of funky shit going on in the blue area that you can take advantage of if you want to, but we don't have much time here. And that says, that's the end of memory right there. I don't know, this little cutoff there. So let's talk about the Z80. Well, no. I'll talk about the VDP with this squiggly, since it goes up there. All right, so this is the VDP. This is where the squiggly comes in. And again, we talk to the VDP through registers. The VDP has 3 areas of memory, all of which are entirely used and have no real map. These definitely have no map. They just serve one purpose. VSRAM controls scrolling up and scrolling down. CRAM, versus kind of like saying, I say cram all the time and no one knows what I'm talking about, controls the colors. So you can have 64 colors. Raise your hand here. Who likes colors? It's the entire crowd. You don't like colors at all back there. Are you maybe colorblind? Never mind. Don't want to offend anyone here. Colorblind. It has 64 colors from a palette of 512. It's 9-bit, 3-bit associated with RGB. So that's what's stored in CRAM. It's stored in kind of a funky way where it's not one after another. There's a gap there. I'm not going to talk about that, but it's not mapped as you would think it would be. Just keep that in mind. Think and it with E a lot. That's it. So if you ever do it, just and it with E a lot. You'll know what I'm talking about. Then this serves a number of purposes. It's VRAM. It is 64K, like the actual RAM. It serves these purposes. These aren't mapped anywhere. They're controlled with registers, which you set using the 68K, using those 2 addresses. You have scroll A, scroll B, window, HScroll, and Sprite, the Sprite attribute table. Scroll A and window are connected. I'll talk about scroll A. Scroll A is a plane of 8 by 8 pixels that form a sprite. This is what we talk about when we talk about sprites. We have this 2-dimensional array of pixels, and that's a sprite. So you have a number of sprites. They can be a number of variables long and a number of variables high that compose a 2-dimensional array of these sprites, and that's called a map. Think characters on a screen. You can have characters next to each other, and if you think of every character, A-S-S-H-O-L-E, being individual sprites, that's pretty much how you'd think of it. So, yeah, so if your terminal is 80 by 25, that's 80 by 25 sprites. For the Sega Genesis, you can have terminals of 32 by 32, 64 by 32, 128 by 32, and then 32, 64, 128. But you got to be careful to not exceed the barrier of VRAM. You can't have 128 sprites by 128 sprites because you can't store that in there without clobbering all the other shit. So, Windows is the same thing. But window and scroll A are connected together in a very special way because you can have registers in the VDP which, based on different areas in the screen where you're drawing, can replace all subsequent drawings of pixels with what's in window. It becomes like this window that you can show. And I'm not going to talk about window either any further, because I don't really use it, and I haven't really seen too many games that do. You can use it, but we haven't gotten that far. Scroll B is the same thing, doesn't have a window associated with it. HScroll is an area of memory that controls the horizontal scroll of every line, or every 8 lines, or the entire screen. You have 3 different modes to do this. And you select those modes with a register. VSRAM is the same thing, but for vertically. You can select the entire screen or every 2 16-bit pixels, every two patterns, excuse me there. And the reason for that limitation is VSRAM is only 80 bytes long, and you can't have every line because that won't fit there. So let's talk about the Z80. And if you can't see, this squiggly goes to a TV because it's connected to a TV. that's the Z80. This is the picture I made last. It looks a little bit different, but it has this little area here, and I should have labeled it with the other one. But this is the map. It's similar to the 68K in the sense that everything's pretty much static. You have memory at the beginning. That's where it starts. There is no real interrupt table of sorts that it starts from. It just starts from 0. And you got to look out for that. I thought it started at 38, so it starts at 0. This little area here represents these, and these are connected to the sound chip. I'm going to be talking about video, and my friend Luis here is going to be talking about sound, and we're going to try and do half and half here. So I'll leave those a little bit to him. I'm going to talk about the bank switcher a little bit, though, because the bank switcher is a special area in memory where you store 9 bits sequentially, one after another, and those 9 bits become upper bits to where this area of memory, the 68K bank, is in the 68K. And that's 32 kilobytes. That's half of the Z80 memory, that little area there. And you can go and put the upper bits and have that be associated with any area in the 68K you see fit. That maybe does not include ROM. I've done some tests, and there's documentation that says you can do it in ROM, but I can't get it to do it in ROM. So not exactly sure what's going there. We can easily do it in RAM and everything else, and you definitely can't do it on itself and have this infinite memory loop that explodes your Sega Genesis like it does to the Nintendo in every commercial you see. So let's talk about the registers. These are the registers of the VDP. This is my ASCII PowerPoint presentation here. I should have explained that. Okay, I showed you two areas of memory that you can write to in order to control registers. You can do a number of different things with those two registers, with those two addresses, not control registers alone. You can do DMA transfers from VSRAM to VRAM to CRAM to VRAM. You can copy between them. You can do it from 68K RAM to VRAM and all sorts of stuff. And again, supposedly you can do it from the 68K ROM address of the 68K RAM into VRAM just fine, but I haven't quite got that work to work either. So mode set, I'm going to speed it up a little bit here. Mode set 1. I have a library that I wrote, so I'm going to reference macros and variables in the library that you can use to set these pretty easily. This is the define for mode set 1. It's register 00, and all I have to do is write to one address to set that, because one address for those two addresses to set that, because that's how those addresses work, and I'll get into that later. Display enable, start the beam, all sorts of things, just turn it on, turn it off. Palette select, you want that always to be 1 pretty much. There's some monochrome funky shit if you have it 0, but I haven't explored that. So 1 has color, 0 has monochrome. Horizontal interrupts, the Sega Genesis can generate 3 interrupts, a horizontal interrupt, a vertical interrupt, as well as an external interrupt for the controllers and other such things. And those are on the auto vector interrupt tables if you've used the 68K of the 68K. Then we have the rest are zeros. And those aren't all necessarily zeros. I don't use them. You read the documentation. There are other things, but I don't use them myself. And holy crap. Yeah, it doesn't work because the projector sized it differently, so I can't do page down. So, all right. Mode set 2. Have that be 1. Set it to Genesis. This is for backward compatibility with the master system. Just have it set to 1. PAL, have it set to 1. This is inversed. I should have wrote PAL first, but 1 equals NTSC. You can use NTSC. You can use those defines for that. DMA enable. If you want to do DMA, set it to 1, because you might accidentally write to the VDP addresses to start DMA. That happens a lot because the documentation for writing to those really stinks. And it's almost trial and error when you start to do it. Vertical interrupts enable, show display. The first one generated the scan line. This one just blanks the display. Vertical interrupt still goes, Still pretends like everything's going fine, you just don't see anything. With the first one, with mode set 1, turns everything off. Set it to 1, backward compatibility. Name table, scroll A, base. It's kind of a long define. I want to shorten these up in the future. You have a register. It's associated with these bits in a 16-bit vector. That vector, the VDP guy that I showed you with the VRAM and all the associated areas, that vector represents where in memory that is going to be. So this is scroll A base. Where do you want that in memory? You can only have it in memory where these bits are valid. You can't have anything below that, so you can have you can't have a fine linear wherever the fuck you want. But use scroll A, that macro, and put in an address as you would, and it'll convert it to that. Name table window, same thing. Pretty much the same thing. This one, it's mapped a little bit different, so if you want to do it yourself, just keep in mind that it's mapped a little bit different. And again, that's scroll B address. And I'm going to come to me at 9. I haven't burned the CDs yet, but I'll burn everything that I have up here, the demonstrations and everything on a CD, so including the slides and everything. And the video. OK, Sprite attribute base. Same thing. I'll get into the Sprite attribute base a little bit later, what that area of memory represents. Background color, one of 64 colors. You have 64 colors. You have 4 palettes of 16. Each sprite can have 16 colors, but each sprite can be selected from one of those palettes. So you don't have true 64-bit color throughout the entire screen at a pixel per pixel level. It's an 8 pixel per 8 pixel level. And you don't have 16 colors either, because color 0 is transparent. There's a priority to how the Sega Genesis draws pixels. And if it's transparent, it goes to the lower priority thing that needs to be drawn. I'll talk about that now. The priority is this. You have a background color. If everything's transparent, it goes to the background color. You have scroll B. If everything's transparent, it goes to scroll B. You have scroll A, goes to scroll A. You have sprites, goes to sprites. And then you have another bit associated with each sprite called a priority. If that becomes 1, then that is above all of these. So you can have plain B with a priority of 1 that's over sprites, and so on and so forth. And that's how the priority works. If you read sega.doc, they have 4 pages devoted to displaying little pictures. No, it's all crap. Just keep that in mind, and it's not that complex. H counter. It doesn't generate a horizontal interrupt at every scan line. You can have it generate an interrupt at whatever scan line you want. You wanted at 16 scan lines? Well, it can do it. You just write 16 there. And it generates the interrupt at every 16 scan lines if you want to do something every 2 sprites or something like that. Mode set 3. These 2 bits represent the size of the H scroll, whether it can scroll every cell. The documentation says cell and everything. They mean sprite when they say sprite, so every 8 pixels, or every line. And I didn't write a macro or a mask rather, for the screen, because that's 0. So 0 is the screen. Same thing with vertical scroll. You can do it by screen or 2 cell. That's 1 bit. You have 2 options. External interrupt, enable. There you go. Mode set 4. The screen can be 40 or 32. My friend Luis brought up a very interesting idea of emulating a Nintendo on the Sega Genesis, which is kind of cool because it can be 32. The sizes work out. A lot of stuff works out, so maybe you could. But it could be 40 cells by 32 cells. And I'm going to skip the rest because I'm running a little bit low on my section. So that's pretty much it. Let's see what we talk about next. I'm going to go to one of my tools. This is a Sprite editor. And it might be full screen with this resolution, so that's good. I'll just go mega. There we are. It's kind of neat. I had a lot of fun with the GUI. There's you can do drop shadows and stuff like that. And I wrote a library for the GUI, so I don't know if you can see the drop shadows, but they're there. And if anyone wants to write me documentation, I would be your best friend forever. Because the documentation just says, fuck this, I don't want to do this at the end. So that would be very, very helpful. These are the 64 colors. Let's set up a color. This will be green. We'll draw a line. And you can treat it like a frame buffer. You can select what you're drawing on. This is scroll A, and it draws the patterns for you. This is a representation of the VRAM. And patterns are a special thing in VRAM that just starts at 0. That doesn't have a vector associated with it. The patterns just start at 0. That way you can reference them just with a number as opposed to a number and a vector with different things. All sorts of other information. Let's save this. So you can save it in a number of ways. I'm going to save it just as a VRAM binary, and I'm going to save that in temp VRAM. OK, temp VRAM. And we'll go to VRAM. Shoot. Let me look at that for a second here. And this is a cool thing. If you have VRAM dumps from emulators or anything like that, you could just load it directly. So you can load up Sonic the Hedgehog, and it'll show it per pixel. I just want to see how long this is, because we're going to write a program for it. It's to A. So that's sprites all go to A, and we're using, it defaults to scroll. A is at C000. So let me dump those out of the VRAM using our friend DD. And I believe that was AA, was it? No, A00. Pretty sure. A00? Yeah. Sweet. OK, thank you. All right, that's the patterns. Now, E00, for a quick reference, is the size of 64 by 64 Sprite scroll data. So you'll use that a lot if you're dumping things. Skip. I've had a problem where I can't type when people are looking at my keyboard. It's kind of weird, so bear with me for a second. All right, so that's that. I'm going to run length encode them, because I have a run length decoder in the library, and I just want to use that because it's quick. So pat to pat dot RLE. Oh, fuck, I overwrote scroll, so let's write that again. OK, so there's those two things. I have a little Perl program to convert those to headers. Constant U8, pat.rle to data.header. Same thing with scroll. OK, for this, other parts, I'm going to actually go to here. No, not there. You know, I don't think we're going to have time to write a program, so I'm not going to write a program. I'm just going to show you a few programs, and I'm going to go through the lines of code, more or less. It's kind of boring, but I'll show you on Fire, because it's a pretty simple program. And you'll see kind of what we're doing there of Fire. And, oh, Fire. You'll see what we're doing. Start. Since the 68K is fucking elite, you have the user stack pointer as an interrupt vector. It's not an interrupt, but it loads it up straight away, and you don't have to set up a stack pointer if you don't leave supervisor mode. And we don't leave supervisor mode in the 68K in the Sega Genesis, because there's nothing really to secure. As you're not going to run Linux anytime soon on it. There's no memory management unit or anything like that. We have the auto vectors here. External interrupt, horizontal and vertical. IncGen bin, this is a special binary. I have tools that on the CD2 to generate that binary. It just has information for the actual ROM that boots. It reads that information. And a lot of emulators too. Think of it like as an INS header if you write Nintendo stuff. Security shit, jump main. That's it. You don't have to do anything else. This just sets up the auto vectors so you can call them. And these are the interrupts. Push stuff on stack. Jump to vertical hook, which is a pointer to a function. Vertical hook, horizontal hook, and external hook. So let's go to main. Main's real simple. Header for the library, horizontal scroll buffer, because you have a limited number of writes you can do to VRAM while the thing is drawing on this screen. You have more writes while the thing is on a vertical blank. But you can do DMA, and it's real quick. So that's the quickest way to do it, and you can take advantage of being able to write to more VRAM that way. So we have HScroll in RAM, pretty much, as told by the compiler. And if you want to come to me, I'll tell you how to set up the compiler and everything like that. Blank chips, just make sure everything is 0. No routine, that's a function that does nothing. Gen on fire, that draws a Genesis on fire. It's actually part of a demo. I'm not going to do the demo because I don't feel satisfied with it. So let's go to, no, that's cool because I'll tell you about it later. So this is Gen on fire. Set shit up, set the modes, set up where the scroll bases are, C0, that sort of stuff, blah. Write to VRAM, this is a little function, writes run length encode to this address from here, and the size is this. No routine, we have a vertical interrupt. Fill HScroll buffer with a 0. This is a macro that's in main.h. Screen on. That sets up a number of registers to turn on the screen. And I won't get into the rest. I'll just run it. But that's how you'd set it up. If you turn the screen on at that point, you would see whatever you drew on the editor. So I don't have time to get into it. Make clean make. Run gen rom.bin. Now I don't know if this will dump me into kind of a weird mode or anything like that. That's the Genesis on fire. It's waving the HScroll buffer with a sign table. And no, not yet. I was just wondering what the time. Okay. It rotates the sign buffer with the sign buffer, the HScroll. This is plane A. This is plane B. This is plane B high. Gets drawn over everything. So you can have that wave. You don't wave that. I'll show you another example here. And actually, that loads up another emulator, because I have a script just to run like 3 emulators. I make sure things run right. So this one is a little bit more complex. I don't know if you've ever seen 3D on the Nintendo. I know there's Virtual Racer, but that used a separate chip in the cartridge to draw polygons. So this is just using software that kind of jiggles and that rotates. And this is sprites, the scroll B, scroll A, and no, scroll A and then scroll B behind jittering. And the source code for these are going to be in the little CD. If you come to me at 9, because I don't have it burned yet, but if you come to me at 9, I'll show you. This is kind of like a little mini game. So you can jump over that. You can jump over the keyboard. Oh, God. Commander Keen has to jump on those. And Commander Keen turns out to be a dick. You could just set him there, and he'll jump forever and score points forever. So scroll B is in the background. I have kind of a parallax thing, because we can control it line by line. That goes slower. That goes faster. That goes faster. And holy shit, that goes a lot more faster than everything else. So, oh, he jumped into the air. That's a bug. You can't jump while you're jumping. So It was part of a demo. Like it was very specific. It was going to actually be played out by the demo program, so you wouldn't play it. So it's not full collision detection or anything like that. So I'll show you the data for one of those at least. I'll show you the VAX. And I'll put the source code for the not working demo too. You have a lot of art examples and stuff like that. So that's the VAX. You can see it all here. These aren't the map, that's just on there. I have a separate map. So that's just so I know where the sprites are and it gets drawn right. So you can scroll each plane individually if you want. There's plane A. And the score doesn't get scrolled, it just stays there. And you get the idea. I know it wasn't really complete, but let's see how much time I have left here. But now we get into audio, and come up to me because if you have questions, I'll let you know. And we should get people running and making programs. And I want to add one thing though before Luis begins to speak about the audio subsystem. If anyone wants to write a demo, and anyone wants to work on art and work on sound, come to me, preferably before the demo party is over. We'll come up with a demo group name and we'll write a demo. I'll do code for next year. That way I afford the opportunity to build the tools better and stuff like that for your use. So, my friend Luis, in a minute. Thank you.
Hello. Hi. My name is Luis Gonzalez, and I'll be talking about a little bit about how the Genesis audio works. I'll plug in the audio source. Let's start that right. Okay, a little background of myself. I'm a third-year student at NYU. I have no electronics experience before starting this project. I couldn't tell you the negative side to a capacitor. I started this project about 5 months ago. So these are my adventures of creating and learning about how the Genesis, this little device, how it produces audio, more at the hardware level. And I got interested in video game music. What video game music are these little files. I'll start a playlist so you can hear what they sound like. Video game music can represent many things. It could be NSF files, which what you're hearing right now is a Nintendo NSF file, a small 19K file. They're the soundtrack. Some of them contain like the ROM information from the game. Others contain a log file of all the registers sent to the sound chip. There are multiple different formats. The one I was interested in is the VGM, which records the log entries to the Sega Master System and Sega Genesis. There are other formats too, like the SPC, which is the Super Nintendo. These are very small files. This one you're hearing is 68K. It's the format similar to like a mod file. And SID, very popular. But for the purpose of this presentation, we're going to be focusing on VGM files, which is what you're hearing right now. Now, VGM files actually have the register information for both of the audio chips in it. It is also the format for the master system, which is an 8-bit version of the chip. You know, you could get BGM files from many sites. One of them is Project 2612, which has like every Genesis game soundtrack. Also, you can get it from SMS Power, which created the VGM format and has Master System soundtracks. And what inspired me to research the Genesis audio was all these projects that I saw online. Particularly was this NSF player, which is a hardware NSF player. It's like a self-contained circuit that plays back a file. And there's these other projects, like the people playing around with the audio chip of the FM chip, the PSG chip, so I thought, why not make a little Walkman-like device that can play VGM files? You heard Sonic the Hedgehog playing back on this player, but it's actually running through an emulator, so some of the things don't sound exactly quite right. So I wanted to create a little player that would play back the audio 100% perfectly, and what better way to do that than to use the actual chips. All the information is online. I have the schematics, the documentations, the data sheets, the VGM formats all spec'd out. I have all the music files. So all I have to do is just put it together, and having no electronics experience, it would be quite interesting. So this site, mudocs.org, has all the documentation you need, the schematics, the data sheets for all the sound chips. When I first looked at this, I had no idea what I was looking at, but it looked pretty cool. Pinouts for the FM chip, the VGM spec. And what led me to believe that I could do this project is there's this text here that says YM2640 write value DD to register A. So I remember seeing that before. I saw it on this pinout. You see it says write to part A register, write to part 2 register. It maps to that VGM file format. So I thought there must be a way to get this file directly to this chip. And apparently I was right, so it led me to create this device that streamed the VGM file data to those chips. And in doing so, I learned a lot about how the Genesis creates its sound, and I'll play back a little sample for you. This circuit took about 5 months to complete. It's running all from battery power. I keep all the VGM information on these little EEPROMs, which are 32K worth of information. So I'll go into the details of how what I learned. We can start with the PSG chip. That's the simplest chip to learn. It's found in many game consoles, arcade, computers. What you're seeing here is the Sega 1000. It's also found in the Sega 3000 Mark III. It's also in the Game Gear. It's a very popular chip. It's in the ColecoVision. It's in the Sega Master System, and of course in the Genesis. So I thought this was a good place to start to learn how this chip produces audio, how to get data into it. The data sheet gave me this information, has 3 square wave tone generators and 1 white noise generator, which sounds like static. Here's a little sound of the chip. This is from Sonic the Hedgehog 2. It's the PSG playing in the background. You hear it so light you don't notice it. Very muted, but it's playing in the background of Sonic the Hedgehog 2, Emerald Hill Zone. Sounds very similar to Nintendo. So to get sound out of it, you write registers to it. This one's playing back. So that's what the PSG sounds like. It stands for Programmable Sound Generator. It's an integrated circuit with everything you need in it. It has an audio mixer, has a built-in oscillator, so all you need to do to get data out of it is write to each of the pins. So how do you do that? See, these boxes represent a channel. This represents one of the tone channels. There's 3 square wave tone channels and a white noise generator. And to access those, you write binary on, off, in just 1 byte to access each of those channels. So depending on what you write to the chip, you can turn off channel 3 volume or set the frequency to a higher setting. I'll go into this registers later. How do I know the PSG chip existed inside the Genesis? Well, it was inside the schematic. You can see the PSG chip here and the FM chip here. I didn't know the PSG chip existed until I saw this document. They both mix into this circuit. Mono, stereo, mixes into the headphone jack. So I thought this was great. How do I get data into it? Well, the first thing I needed to know was hex to binary conversion. The image you see on the left in red, that's the VGM file data. That's the instructions in that file that has all the music, register changes you need to do, set the channel on or off. And these pins, you remember that pinout has D0 through 8. So just take those hex values, convert them into binary, and just map them to the correct pins. Just dump them like a player piano. How do I do this? Well, there's this tool called Arduino which let me do that very easily. Its IDE is very easy to use. It lets me control this microcontroller, which lets me to set these pins, digital pins on the top, to on or off very easily. Like you can see in the code, digital write pin, set pin 6 to 1. So that's the first prototype I did was to stream a VGM file through serial port, send it to the Arduino, parse it out into the 1s and 0s, and send it to the PSG chip. I got this idea from Little Scale, this website that did a similar project. And here's a video of it playing. So from my computer, the VGM file streams to the serial port, USB. So it works. Problem was, I ran out of pins. To implement the VGM player, I'm going to need the other FM chip, which has more pins than the PSG chip. As you can see here, this is all filled up. I don't have any more pins to write data to. So I had to look into shift registers. What shift registers allow you to do is send more data out using fewer wires. So you remember the byte example I showed you? You could fill up 8 bytes just directly connecting the pins to it. Well, in this example, you take one bit and you push it out one at a time. So if you can imagine, I fill a bit into this box over here and then move it over to 6 and then push another bit, 0, push it over, and it keeps going, keeps going. Once this is filled, it moves on to the next one. So with like 3 lines, you could send 16 bits of data. So this is a shift register example that I just used the Arduino examples from. I put a ZIF socket in there, so that's where the FM chip was going to go. And these lights will tell me if I'm streaming the data out correctly. The order matters. I put them in reverse. So these are the shift registers. This is the PSG chip. It sends the data out to this shift register. It fills 8 bits here. And then once this is filled, it sends 8 bits to there. And then it sends another like latch command to tell it to send it out all at once. This means it's going to send one byte to the PSG chip and 1 byte to the FM chip. This is where the FM chip is going to go. That brings me to the next step, to getting the FM chip. And to do that, I had to take one out of a real Genesis. So this is the Genesis I took the FM chip out of. I had to desolder it. This is a picture of all the steps that I went through to get it. I bought a used Sega Genesis for like $30. Took it apart. Very painful to do because it was a nice system. Took out all the parts. You can see that's the cartridge port. That's a 68K CPU. This is the chip I needed. All these are like memory chips. So I located it, I desoldered it. I have it in my hand. Now, straight to the breadboard. Now, the FM chip works almost the same way as the PSG chip does, and it means you could get sound out of it by writing bytes to it. What those bytes do, if you read the documentation, they're different register writes. Like we'll take a look at the pinout again. These values D0 through D7, that's where the bytes are going to go. And there are other pins that tell you which part of the registers you can write into. This chip also has an integrated audio mixer, which was convenient. Has stereo out. These are 2 stereo outs. And these 4 pins tell the chip that it's ready to receive data. If it's gives a status if it's ready to receive the next set. This is what a VGM file looks like. Remember those hex commands that we needed to send those bytes out to the pins? So now that I know how to send bytes to the IC chips, it's just a matter of parsing through this file. If I encounter a command, like 50 is a command to send the next byte to the PSG chip. 52 would be a command to send a byte to the FM chip, so on and so forth. What those bytes mean, you could read the documentation and kill yourself understanding how the channel addresses, but you just pump it the data. A little overview of how it works. I keep the VGM data in this EEPROM. Takes it 1 byte at a time through the Arduino. The Arduino sends it out to the shift registers. If you remember, the shift registers is just containers of 1 bit at a time for 1 byte. So I fill these up. They all have 1 byte worth of information. This one goes to the PSG chip. This one goes to the FM chip. And these are little control bits that you need to tell this FM chip that it's ready to receive information, it's ready to write information. You need to set the clock low or high. And it receives the information serially, and then it receives a latch command to send it all at once. These are oscillators, 3.5 megahertz for the PSG chip, 7.6 megahertz for the FM chip. And I told you earlier that the FM chip has an audio out, so does the PSG chip. They all mix into this headphone jack. The bottom right is a little Arduino chip, what the headphone jack looks like, a little EEPROM. That's the first prototype. This is the code that was necessary to interpret the VGM data stream. Like when you encountered a command that's, say, a 53 byte, that means it's going to write port 1, register AA, write the next byte that's next to the 53 byte. There's all kinds of resources you can find online to help you understand what the chips are capable of. I went to Project 2612 to download all the VGM files I needed, SMS Power to get the VGM file spec. Sprite's Mind is a forum. It's an active forum where people actively create Genesis programs or any technical questions or demos or music that people create nowadays. There's a Facebook group dedicated to the FM chip. I thought that was pretty cool. I joined it. There are trackers available. Trackers are music creation tools. These output VGM files. It's popular. I think that there's a chiptune community that creates VGM files. There's multiple VGM editors. There's one for the PSG chip, 3 channels, 1 square wave. This is another Genesis tracker. A little player. The Winamp plugin that I use came from chipamp.org. It installs a plugin that lets you play back VGM files. And I think that's it. I'll play back another VGM file of the circuit. You could hear. That's just the PSG chip, no FM. Someone made that for a chiptune composition like 2 years ago. It's about 20K. I didn't implement all the instructions, all the timing instructions correctly, so it's a little off. You could hot swap it. Last one. This is a song that someone created using those tracker software. It didn't come from a game. Okay. And that's it. This is my circuit, self-contained. Thank you.